Today we'll be going for in contextual languages. We'll go for simplification of CFG, context-free grammars. Okay. So what we have is we have G, V, sigma, PS. Then I'll be going for V dash, sigma, P dash, S. I'll be looking for this. Okay. Uh, in some cases, it may also be improved. So what will be that? G dash will be the simplification of G with the condition that whatever language generated by G must be same by G dash. So this will be the condition. Okay. That means what you can say is that G and G dash are equivalent. Okay. The reason why we are going for simplification of CFG is that reason is very simple, that when you go for constructing the grammar, each of you can construct grammar differently. So that means as far as production set is concerned, then there may be some sort of redundant rules maybe within this production set. Okay. And that may lead to the complexity also. So what we are looking for this simplification is that we want to minimize all these redundancies. We also make use of many unit productions. There are some nullable productions also. So such production rules must be simplified. And obviously out of that you will see that you may actually introducing some useless symbols also. Symbols, it could be terminal, it could be non-terminal as well. So in view of simplifying all these, that we want to simplify the production rules for unit productions, for nullable productions, and then obviously we are also looking for simplifying the useless symbols within this production set. So, and this is the this is what we have is that certainly this is given grammar G, and we are producing this G dash. We are actually V may be becoming now V dash, then sigma dash, then P dash. The starting symbol will be same always, in such a way that the language generated by the given G should be same whatever language generated by the improved grammar. So this is what simplification of context-free grammar talks about. Now, so we have talked about this. So what we do is that that we are looking for useless symbol removal, then we are looking for unit production removal, and then we are looking for null production removal. Okay. So these three actually requires for the simplification, that you need to remove the useless symbols, you need to remove the unit productions, and then also you have to remove null productions as well. Okay, this is what we do. So we'll start with like what is useless symbol, how will you declare any symbol as a useless one, and then certainly we'll go for unit productions, null productions. Unit production and null production is when you talk about unit production, then when we talk about like this is referred as unit production, where actually you are on left hand side and right hand side both includes single non-terminal. Okay. Whereas null level production says that this is null production, where actually a non-terminal produces empty string. Okay. Not only this, if you have say A, B, and you say that B epsilon, in such cases, even this A is also having null production. The reason is the moment I say B actually produces epsilon string, then this may be replaced by this and A. So this too becomes your null production also. So both A and B are nullable variables. So okay, now removal of useless symbols. Okay, then you can write a symbol is useless if it doesn't a symbol is useless if it does not take part in the derivation of some string in the language. Okay, so this is what define the useless symbol. So the first point is a non-terminal symbol, say A, can be useless if there is no such that this. A non-terminal symbol A can be useless if there is no W, small w, which is actually some string out of this sigma star, such that this. That means A cannot produce this string, W string. Okay. A cannot produce the small w string. Okay, so then in that case A will be referred as useless. Okay, fine. Such a non-terminal is called non-generating. Such a terminal is called non-generating. So this is first. So we have non-generating symbols. Now next is a symbol, terminal or non-terminal, is useless if there is no way of reaching the symbol from the starting symbol S. Okay, that means if you cannot reach from S to any of the terminal or non-terminal, like if I say that suppose what you can write is that S is AB, B is AC, D is say C, if I say like this. So in this case, certainly you can see that I can reach A, B and even to C also, but S cannot reach to D because there is no such production rules so that S can use and can reach to D. So in that case, this D will be, and similarly for, like suppose you say that D is this, then in this case also S cannot reach this small d. So in both cases, terminal and non-terminals are useless. Okay, fine. So that is what we call it. That, or you can write, suppose we never have this okay. That means you cannot generate this. That means S starting symbol with 0 steps or more steps If you can reach to this, then this is not a useless one. But what we are saying, we never have this. So that means we cannot generate this part for any case from starting symbol S. So this A could be referred as useless. Such symbol is called unreachable. Okay. So there are two cases of useless symbol. One is non-generating and another one is unreachable. Okay. So let us go for devising sort of algorithm through which we can eliminate these useless symbols out of the grammar. Let us go for algo for unreachable symbols. Algo for unreachable symbols. So what we do in this case is that we try to find out sort of all unreachable symbols and we'll keep it in one set, and then like what you have is this. You have G, V, sigma, P, S. So you have production set rules and all. Using this production set rules, you have to identify unreachable symbols. Okay. So what you do is that, say, I'll produce some sort of this R, which is nothing but it is a reachable symbol set. That means it is very easy to find out the reachability. That I can start with S and I can always prove with the help of production set rules that I can reach these. So apart from all such symbols, the rest of the symbols would be considered as unreachability. So what we do is that I'll find out all reachable symbols and then I'll just go for this. That means you have V set, difference of R will actually give you the unreachable symbols. This is what we do it. Okay, this is what we mean it. So how to find out is very simple. That you can start with this. Like suppose you have production set rules. There are so many rules you have. Okay, you can start with S. Say S is having SA. Okay. Now inductively go to all the production rule and see that how far you can go for this. Obviously, the moment S defines A, that means A is reachable. So my R set will start with A. Okay, fine. Now, if suppose A defines BC, there is a production rule in this. Okay. So obviously, S can produce BC. Now this set becomes BC, B comma C. That means A, B, C is reachable from S. Fine. Now similarly, you go for like you inductively scan all these rules and see whether you can reach from S to those symbols or not. Suppose there is some case that E defines H is there. I cannot reach to this E, then certainly S cannot generate, cannot go to this E. So that in that case, this E will not be in the set of reachability. Then whenever you will go for difference of this, because this E is already in V, because it is in the grammar itself. So that part will go. So what we do is, let us go for the algorithm. We can actually, this R is nothing but the set of reachable symbols. The set of reachable symbols. Okay. So what induction you can go for? Suppose A belongs to R. Okay. A belongs to R and A alpha is in P. Say B in alpha is also reachable. And hence this R will so what we have is, initially we start with this. So what you have is, like, if you go for the induction part, R always be this element S. Okay. So this A could be S, because starting symbol always be in R, because that is the symbol which is reachable with anything. So this A could be S also. So S belongs to R. Now, if any production rule of this type holds, okay, say S belongs to A, B, this holds, okay, then this A and B, this, or you can write like this, A and B. So this R set will be updated with this. Now, what you have is, you have now, as per this algorithm, you have now A and B. Now again scan your production rule. If any of the production rule where actually left hand side is A or B, then right hand side whatever symbols are there will actually be updated with this. So similarly, it will inductively, you will go for it. And at last, when you exhaust with all the process, like in 2 iterations, you are not getting any changes, you stop it. Okay. So at that point, whatever R you are getting is the set of all the symbols which is reachable from starting symbols. Okay, fine. So what you do is simply that unreachable symbols you can get unreachable symbols will be nothing but V minus R, isn't it? V minus R. That means V is having the given grammar all symbols, so it is basically including reachable and unreachable symbols as well, because your definition is having some wrong. So once you get this reachable symbol set, minus it from this, Whatever symbols comes will be the unreachable symbols. Fine. This is one algorithm for this. Now, the same algo can be used for terminals also, because you have this sigma set. Okay, you can generate some set, maybe say state T I can write, okay, which is nothing but set of reachable terminals. And as same we have done in case of non-terminals, same way, same algorithm will carry on, and then at last unreachable terminals will be nothing but sigma minus, isn't it? Same way, like you have say S goes to A, then A goes to B, sorry, A goes to A, B goes to B. Like if this is there, then certainly same algorithm which we have, certainly you can start with this, that this is, this can go to A. So A is my reachable terminal, okay? But you cannot reach B, small b, using this S by any means. See, always, let me tell you one thing. It is not necessary that always S will generate A single-handedly. What I am saying reachability is that if S is generating like this, say A, B, C like this. So in this case, all four symbols, whether it is terminal or non-terminal, is reachable from S. Okay, so reachability means you are supposed to generate such a intermediate sort of expressions where actually terminals and non-terminals are involved and can be reached through S. Okay, not necessarily that always you actually converge to a single terminal or non-terminal. It is not necessary. Okay, fine. So that's the thing. So the same way you can generate this terminal strings, which is useless. The next is algo for non-generating symbol. Okay. In this case, terminals will not be there. This will be always be non-terminal. So we only look for non-terminal in this case. Okay, fine. This also be done with the help of the same set of algo. Only the thing is the way we can define like this, that identify the set. Say I am defining this as set G. This G is nothing but the set of generating non-terminals. Okay, set of generating non-terminals. This. Oh, sorry. Set G. Okay. the set of non-generating terminals. Certainly we can define this G inductively. How? Suppose A is W, where W is this. This is there. Okay. So I'm just removing this part because I have to write more thing on this. So we start with what we call it as base, that place in G all A belongs to V such that sigma star is in T. That means place in G all non-terminals which belongs to V such that A is defining some W, which W is nothing but is a part of sigma star is in T. Okay, this is what first step. Now, inductively what we can do, V defines this, where every non-terminal in alpha is already in G. Okay, like suppose this such production rules you are having, where actually in alpha whatever non-terminals are there is already in G. Okay, then add B in G if B is not in G. That means repeating is not allowed. So if B, add B in G if B is not in G. Okay, and then repeat this process again and again. Okay, so what you get is you will be getting the all such generating non-terminals, and at last when you go for non-generating non-terminals will be nothing but V minus. Okay, this we will get. Fine. This is there. See, what we are trying to do is very simple. Just I'm giving you a simple example where actually you can see. I'm saying that this is A. This is your production rules and all. So obviously this. Then you say that A is B, C. Say C says A, B, C, something like this. Okay. Then B is D, E, and then H is E, something like this. Or you can say that H is D, E, something like this. If I say like this, okay. So this, you can see that obviously this is there. So this is a generating one, and then A goes to B, C, then C goes to this, B goes to this, and then H goes to this, H goes to this, and all. Then when you go for looking for that whether all the symbols which is involved in this production rule are generating or non-generating. or what are the symbols which is non-generating as well. So can you identify that is there any non-generating symbols in this? Yeah. So obviously clearly says this H, because S can go A can go B, C, this can be reached through C, this can be reached through B, but problem is that H cannot be reached by any means. So this H is referred as non-generating because H cannot generate anything out of it. Okay. So this is what we mean it. Now we'll go for removal of epsilon production. So what we do is that you have to remove all salad productions from P. Okay. For example, if I say this is A, this is this is A epsilon and B. Like suppose you have written this, okay. So what you have is simple that you know that this is my epsilon production. Straightforward you can look on this. This is my epsilon production. Now, not only this, we have to see that this can generate others also as an epsilon production. Certainly, if I replace A with this, then it can go for. So obviously this cannot be epsilon production because B can generate B only. So S can generate B, this cannot be. This cannot be epsilon production. So what we have now in this is this. So what you need to do is you have to go for removing this. How would you remove this? It's very simple. Now this is your P. I'm looking for P dash, which will actually result after eliminating this. Okay. So what you have is obviously this will be there. Now since this involves A, replace A with epsilon. If you do that, then S will go for B. Okay. Certainly B cannot be, this is 2 and then this BB is there. So this will be your resultant production set by eliminating this. Okay, this is your production. Similarly, if I take another example, what I mean is, suppose S is A, B, D, okay, and B and D are nullable. That means these are the null non-terminals. That means anyhow, I'm just assuming it, okay. So obviously, what in this case is, that means what I'm saying is this is something as this, not this holds, okay. If this holds, then what will be? This is your P. What will be P dash? In this case, it will be like this. That first go for B to be placed. So first this will be A, B, D. Okay. Now this will go for, if you place B here, epsilon here, you will be going for AD. If you place D here, you will be going for AB. If you place epsilon BD both, you will be going for this. So this particular set can be replaced with this particular set. Actually, what is happening in this case is that this epsilon is always actually used to terminate the generation, okay, at some point. Okay. So when you look for elimination of all these such production rules, what you do is simple, that you generate all such combinations which is required for particular set of strings to be generated. यानी कि simple है. What you need to do is that suppose you want to terminate somewhere where actually you look for that this B should be replaced by epsilon. Like suppose what you have, like suppose generating say a to power n. Okay. So what you do is that repeatedly you are just generating such symbols. Like suppose what you do is that S A A. Okay. And you are saying that A is epsilon. So what once you do that, then S can be A A A. It can be A like this. Whenever you want to terminate this, you use this. So it will be epsilon and it will be AQ. Now what will happen in this case? If you go for this, then for this case, if I go for this, what will happen is that you want to replace this. If you want to replace this, then what will happen? S will be this. So now, if you go for the same set of generation using the simplified or this particular after removal of this particular epsilon production, what you need to do is that it will terminate one iteration before itself, because that now S can generate also A. So instead of generating this epsilon, I'll go for this, and obviously what will happen is I think I have put wrong example. I can write like this. I think that would be better. This. So what will happen in this case is that The first case, it will be like this only. The next case, whenever you go for this AS, then AAS, now will not go for this. Rather than I'll use this one and I'll terminate here itself. So in this case, it takes 1, 2, 3, whereas in this case, it takes like generating this part 1, 2, 3, 4, whereas in this case is 1, 2, 3. Only in 3 iteration it will generate the same thing by eliminating this part. Okay, so this is what the changes which will happen, which will come to the place. Okay, fine. So that what you mean is simple. 2 is if A is x1, x2, xk is in P and xi is some or all are nullable, then this will go for yk, where yi is xi or epsilon if xi's are this you have. Obviously, except A belongs to this. Same example just we have seen. Why this? Like so, as I told you that if A is B, C, D and B, D are nullable, then A, B, C, D, then A, C, D, A, B, C, and A, C. All these will be included. Okay. Simply what you are doing is that you are replacing B with epsilon, then D with epsilon, then both with epsilon, and you will be generating this. This set will be generated. Okay. Certainly, you can prove this correctness of this epsilon production also. Correctness of removal of epsilon production. Prove it. I am giving you as self-study. This will be done by induction itself. So do it. Okay. Now, then third one is what we get? Removal of unit production. Removal of unit production. Okay. That means whatever of type this is referred as unit production. This we want to eliminate. Okay. This can be done very simply in that case. Like suppose what you do is that once you like a sequence of removal of sequence of removal of like what you call it as epsilon, unit, and useless is a concern. The reason is very simple, that you'll see that while removing this epsilon production, you will be generating some unit production. Okay, so if you remove the unit production first, then certainly, and if you go for epsilon production removal next, then in that case again unit production will be there and you will not be able to resolve it. So what you do is that first always go for epsilon production. Okay, or I can write removal of epsilon production. Okay. Then go for removal of unit production. Reason is that while removing the unit production, there is always a case that you will be generating some sort of useless symbols. Okay, so that's why before useless symbols you go for unit production removal. And third is removal of useless symbols. Okay, this is what this should be the sequence of removal. Obviously, first you go for epsilon production. The region is very simple. This can produce unit production. Okay. Then next, so whatever unit production is produced by epsilon production removal, that can be handled with this. After eliminating this unit production from this, because the unit production removal can generate some useless symbols, then go for useless symbols. So whether it is originally useless symbols are there or generated by these, can be catered with here. Okay, so in this case you have to go for both the cases, that unreachable symbols and non-generating symbols. Once you do that, then you will be actually looking for what you will be getting simplified G, that is simplification G. Okay, obviously you'll always be the condition that whatever language the original grammar is having, the simplified grammar should also be having the same set of languages. Okay, so that is what we do it. So what we do is we can see with this just suppose you have like this, that you have P, S is A S B, then S is A C A D, and then A is C D. If this is there, okay. So what you need to do is, in this case, that this you have to remove. Okay, this is in your unit production in this case, because you can always see that there is no epsilon production in this case. Now you have to remove this. Okay, removing this, what you need to do is simple, that this involves this. Okay, so this will go for what? What you can do is that this. Is that okay? So that means so this will eliminate this part, and obviously this will be intact and all. What we do is like, so this way you can eliminate the unit production part and all. What next is required is that we'll go for one example, and that will be the one example which will be discussed, where actually you are looking for all three to be done. That means such example you need to go for, where production is having the epsilon productions also, unit production also, and there is a possibility of useless symbols also. So once you solve that, then obviously this epsilon production can generate unit production can generate useless production, useless symbols, and when you perform all these tasks, then you will be getting the simplified grammar. So this will be this particular problem or example. Since I have given the example for each of the cases, this example will be done in tutorial. Okay, fine.